I've got a power supply here on setting 6, giving me about 6 volts worth of DC according to my multimeter. In fact, looking at the oscilloscope, which is really just a fancy precise voltmeter, I get a nice smooth 6 volts. Lovely. Switching to AC, keeping the same setting, the multimeter gives us 6 volts, pretty much the same as for DC. And the oscilloscope, that's over 8 volts. Okay, so not what we're expecting perhaps, but actually that's what this lesson video is all about. AC and DC are different, but we try to use them interchangeably sometimes in the same electrical and electronic systems. So what we need to do is make sure we understand how they are different, and we could do with some maths that's going to help us relate one type of circuit to the other. Let's try to think like engineers. In any electrical system, the voltage changes and the current changes. We produce electricity at one end and use it at the other end. What are we really wanting to transfer down the electrical cables? What do you think? What are we trying to move around? Well, what we really care about is sending energy from place to place, energy to do work. In electrical terms, we normally consider power instead, as it is easier to quantify through P equals IV. So, since power is the key quantity being moved around the circuit, electrical engineers want setting 6 on the power supply to give us the same power, whether it is DC or AC. Now keep that in mind. We want to equate the power in the DC circuit to the power in the AC circuit. In fact, the goal of this lesson video is to be able to calculate the effective DC voltage that will deliver the same power as an AC voltage of a certain peak voltage V0. We call that the RMS voltage. So the RMS value of an AC voltage is the value of DC voltage that would produce heat at the same rate. That's a definition you can use. Next, let's explain it properly. Here's a graph showing a direct current. The y-axis could be current or voltage, since both are changing sinusoidally. Actually, let's separate them out. So I have a blue line to show the alternating current and a green line to show the alternating voltage. Sketch them down yourself. Now if you don't have anything to write on, then A, that's terrible, you need to be taking these lesson videos seriously, and B, pause the video to get something. Right, so sketch the current and voltage plots. Now, on the same axes, sketch the power plot for this electricity here. Hopefully you got something looking like this. Since P equals VI, the power is always positive. When current is negative, so is voltage, so the product is positive. Cleaning up the graph to show only power, it's always positive or 0, and there is a peak voltage labelled P0. But the power is changing with time, unlike DC, so we need to do a bit of maths trickery to compare the two of them. Look at the area here. It represents the energy being transferred, since energy equals power times time. Energy is the area under the graph. If I draw the rectangle around it though, and I shade this bit green, then flip it over, then rearrange the picture a little, and you can clearly see that the area above the line is equal to the area under the line. So the energy transferred by the AC supply, EAC, equals P0 times T over 2, half of the area of that rectangle. If we had DC though, the area under the graph, the energy transferred by the DC supply, EDC, equals PT. Now, what we want to do, remember, is find the value of DC voltage that would produce heat at the same rate as the AC voltage. So, let's equate these. EAC equals EDC. P0T over 2 equals PDC T. P0 over 2 equals PDC. Alright, looking good. But we want to get this as voltage. We're going to use P equals V squared over R. So P0 equals V0 squared over R. And PDC equals VDC squared over R. Remember, we were going to call it the RMS voltage, so PDC equals VRMS squared over R. Subbing them into P0 over 2 equals PDC, we get V0 squared over 2R equals VRMS squared over R, or V0 squared over 2 equals VRMS squared. So finally, VRMS equals the square root of V0 squared over 2. VRMS equals V0 over root 2. Remember, the RMS voltage is the value of DC voltage that would produce heat at the same rate as the AC voltage. On a graph of AC voltage, we can label the peak voltage up here and the RMS voltage here. Now, if we go back to the results I got before, the oscilloscope recorded over 8 volts, about 8.4 volts. So if we divide that by root 2, we get 6 volts. That's pretty close to what the multimeter showed us. So the multimeter was not broken, it just told us the RMS voltage instead of the peak voltage. And it did that because it is more useful, as it allows us to compare AC and DC circuits more easily. Oh, and it's called RMS voltage because it's a square root of the time average of the voltage squared.